Welcome back to the castle. Today what I'm going to try to do is put all of the science that we've looked at in the last 3 videos on this whole concept of the science of precision irrigation. We've looked at a lot of science in the last 3 videos. So what I want to do again in this one is to put that science together and now actually show you how to incorporate that science into your irrigation protocols, whether you're a field farmer or a greenhouse grower or a grow room operator. So I don't want to spend too much time on reviewing the last 3 videos because they were fairly long, but I'll just ask you to go back and make sure that you understand the concepts of the dipolar nature of water, the concept of cohesion and adhesion. Cohesion being the tendency of water molecules to stick to or bind to each other. That's water molecule to water molecule binding. And then we have adhesion, which is the concept of water molecules sticking or binding to non-water molecules. And in the case of irrigation, we're going to be looking at the tendency of water molecules to stick to or bind to the solid particles within the soil matrix. So cohesion, adhesion, and I also want you to recall the science that we looked at in the last video, and that being that concept of the potential energy of water, and that water will have a tendency of going from an area of higher energy to lower energy. We looked at how this is what drives water being drawn from the soil up through the plant and into the atmosphere again. That in combination with the osmotic pressure, that osmotic suction, that osmotic draw within the plant is going to be critical as we now look at putting the science together for irrigation. So we have cohesion, adhesion, we have the concept of the binding of water molecules to the soil particles, to the surface of the soil particles. And we also have this concept of the water potential continuum, water wanting to flow from an area of higher potential to an area of lower potential. So why is this whole area of looking at precision irrigation so critical to us? It's critical on a number of different levels. So we can look at the global impact of water shortages, climate change, the fact that we can see what the impact of drought and the reduction in water tables in the United States and around the world, the impact that has on crop production. So our use of water in a precision manner will help conserve that precious resource. From a more practical standpoint, if you're a field farmer, overwatering or underwatering can have a dramatic impact on both the size of your crop yield and the quality of your crop yield. Overwatering can do a number of different things. It can waste water again, and if you're irrigating, it is a higher demand on your machinery, on your pumps, which means you're out in the field longer, you're transporting equipment on your tractor, your electricity bill is higher, you're probably using more fertilizer because you're flushing nutrients out of the soil. Those nutrients in an overwatering situation can end up in the downstream water stream and end up impacting the watershed for your drinking water, the water in the bays, the ocean. We can cause eutrophication, algae blooms. So overwatering from an environmental standpoint can be very negative. Underwatering can cause a dramatic reduction in yield size and yield quality. It can increase the temperature of the plants, shut down the stomata. So both overwatering and underwatering can be very detrimental, both on the global environmental stage, but also to you as a grower from a financial and a productivity standpoint. So we want to look at using water effectively, efficiently, and precision manner to be good stewards of the land, but also to be good business people. So as we put the science together from the last 3 videos, we could make this extraordinarily complex. People do their PhD theses on the whole world of precision irrigation and how it relates to biological function. We're going to try to bring it down to a level that gets you to the point where you really understand the science, you understand how to use the science in your daily operation, but not require you to have to memorize graphs, memorize formulas, and get so bogged down in the weeds that you're just going to not even attempt to understand, let alone implement the procedures. So let's first look at the concepts within precision irrigation that we have to understand when we talk about irrigation for any plant. We will then move to looking at how we individualize irrigation protocols for the specific crops that we're going to be growing. But first we need to understand the terminology and certain set points and targets that we need to understand, again, when we're talking about any plant. So let's look at the basic language of precision irrigation. When we talk about irrigation, we're obviously talking about controlling the moisture level within the soil. Because as growers, we know that that moisture level within the soil is absolutely critical for hydration of the plant, for the plant being able to maintain turgor, for the transport of nutrients into the plant, up through the plant, evaporative cooling to keep the plant temperature within an optimal range, which is going to regulate the opening and closing of the stomata, which is going to regulate the CO2 inputs into the plant. So being able to have that soil moisture level within the soil matrix is absolutely critical to the whole biological process of having our plants reach an optimal level, which then translates to optimal crop size and crop quality. So the first term that we want to be familiar with is soil water or soil moisture content, which is exactly what it sounds like. It's what the moisture level is within the soil or the grow medium that we are trying to grow our plants in. When we talk about the soil moisture content, we will talk in terms of 2 potential ways to look at and measure and talk about and translate that level of moisture within the soil. The first terminology and the first concept is what we call the volumetric water content. And this is the terminology and the factor that you're probably going to be using the most as you implement your own irrigation protocols, and it's the one that we're going to use talking about the most within this video. So volumetric water content, what is it? Volumetric water content is nothing more than the ratio of the water within a specific measurement of soil compared to the solid particle matrix within that soil. So for example, if I take a volume of soil or grow medium, and this volume, say the column is 12 inches high. If we say, okay, the volumetric water content is 20%, that means that 20% of the volume of this cylinder of soil is water. So we can say a 20% volumetric water content is obviously 20% of that 12 inches is water. 20% of 12 inches is going to be 2.4 inches. So of that 12-inch volume of soil, 20% or 2.4 inches of this column or this cubic foot of water is actually in the form of water. So that's what a 20% volumetric water content measurement would refer to. 20% of the volume of that soil is in the form of water. We're going to look at using a good soil moisture meter, which actually measures in volumetric water content readings. We're going to look at how to use this, how to understand the number, and then to translate that number into your precision irrigation. So again, you have a volume of soil, a cubic foot, a column. If we take a measurement and with a volumetric water content meter and it says 20%, it means that 20% of the volume of that measured amount of soil or grow medium is water. If it's a cubic foot and we have 12 inches of soil, 20% would be 2.4 inches of that 12 inches is water. So that's volumetric water content. And again, that's the number we're going to be using the most when we look at developing your personal precision irrigation protocol. The second concept when we're looking at how much water is in here and how do we measure the amount of water and how do we use that to develop a precision irrigation protocol is this concept of soil matrix potential. And if you go back and look at the video that we just did, video number 3, we looked a lot at this concept of soil matrix potential. And if you remember what soil matrix potential is, it relates to the fact that water molecules are, again, dipolar. They have a positive and a negative pole. That's what causes water molecules to bind together in cohesion, but also for those water molecules to bind to other surfaces like soil particles and organic matter, to bind to those particles and be held fairly strongly. And one of the most important diagrams is the one that I'm putting up now. If you recall, when we looked at it, it shows a soil particle with a pore space with water molecules, and then we can see that the water molecules are bound to each other in cohesion, and we also have water molecules binding to the surface of the soil particle and the organic matter. And we have different zones of the strength of those bonds. The water that's held out in the middle of those big pore spaces is, in actuality, primarily being held just by those cohesive forces of water molecule to water molecule, which are not really very strong. They can be broken quite easily. And as we get closer and closer and closer to that soil particle, the binding of the water molecules to the surface of those soil particles is much stronger. So the closer we get to the surface of those soil particles, the stronger and stronger and stronger and stronger those bonds get. This is critical when we start to understand irrigation in terms of the science, because a plant, in order to get water out of the soil to bring it into the roots and have it travel up through the plant and do all of the wonderful things it does in the plant, it has to develop or create an energy stronger than the cohesive forces outside of the root that will overcome the attractive forces of the water within the soil matrix and actually be able to draw that moisture, those water molecules, into the root. So we have this very basic and very important tension between the soil moisture wanting to be held by both other water molecules, but primarily by the soil particles. This is called the soil matrix potential, or the soil suction, as it was called at one time. It's that tendency of water wanting to stay within the soil. On the other side, we have the root, the plant, which is trying to get that water out of the soil. So the plant has to overcome the holding forces within the soil moisture and be able to break those bonds apart and bring that moisture into the root. So you can see the obvious thing that is going to happen when we talk about irrigation and how to develop a precision irrigation plan. It doesn't take long to figure out that at some point, the forces which the plant is able to create inside, and those forces are going to be driven by both the osmotic potential, and we looked at that in the last video. What causes that osmotic potential, that potential that the root wants to draw water in, and the gradient of water energy potential wanting to pull it up the plant. That can only go to a certain level. The plant can only generate a certain amount of inward pull, but the soil moisture is held more and more and more strongly as you get towards the soil particle surfaces. So at some point there's going to be a point where the plant can't pull hard enough and get that water out. And this is what we as growers have to make sure that we do, is to never get to that point. And indeed, we never want to be close to that point, because as the plant has to work harder and harder and harder to get water out, that's causing stress within the plant. So we have to understand where the point is where the plant can easily get water out, Oh, it's getting more difficult. When we get to that point where the plant is sensing more difficulty, that's when we start having crop reduction and a drop in the optimal growth of the plant. So that's what we're going to look at, is how to understand where these points are in this tension between the plant wanting to pull water in and the soil wanting to hold on to that water. And an absolute key thing to understand is that as the water, that moisture content of the soil drops, the soil matrix potential, or that holding strength, increases. So if we look at those large soil particles, that water that is in these bigger pores is quite loosely held just by the cohesive forces of the water. That water can be picked up and taken in quite easily by the plant. But as that water in the big pores is either drawn out by the plant or is lost through gravitational forces and is pulled down through the soil, the amount of water that is easily available drops and drops and drops, and the water molecules now are closer and closer and closer to the soil particle surfaces, so they become harder and harder and harder for the plant to get out. And if we look at the first couple of videos when we looked at soil structure, remember that the coarser the grains within that soil, the bigger the pores, which means the less total surface area of the soil particles, which basically translates to a lower holding suction matrix within that soil. As we get towards the silt and the clay, where you have all of these sheeted structures and you have a large surface area relative to the pore spaces, the larger area of surface translates to more binding sites for the water molecules, which translates to a much greater, stronger holding power of those soil particles on over the water molecules. So as the water content within the soil drops, the soil matrix potential, the suction, increases. The more you go from a sandy, large particle matrix to a clay, which is that sheeted, high surface area particle structure, the greater the surface area translates to a much higher overall holding, binding surface and soil matrix potential capacity of that soil. So we have volumetric water content and we have soil matrix potential. Soil matrix potential, as we looked at in the last video, is measured in kilopascals or centibars. And like we said in the last one, don't even worry about that. Don't worry about having to remember which one is which. You don't have to go there to understand what we're going to talk about in developing your protocol. We do have to understand these concepts, the cohesion, adhesion, and the fact that as the water content within the soil drops, the soil matrix potential increases, that suction increases, because we have less free, loosely held water within the pores. So what we need to do is understand certain thresholds that exist in terms of soil moisture content between a container or a pot or a field that is absolutely bone dry. If we open up a brand new bale of Promix or Lambert's or Sunshine Mix number 4, or peat moss, and you look at it's what you would call absolutely bone dry, no water in it, you would think that the volumetric water content would be 0. And then on the other end of that continuum, we would have a soil or a grow medium that we have fully watered. It won't hold any more water. If you put water in, it either pools on the top and it just drops through. It cannot hold any more water. We have two ends of the continuum. What's happening in between the two ends of the continuum, and where should we as growers be in terms of our irrigation to optimize the growth for our plants? How do we understand where to be in between these two ends? Let's look at some critical points along that continuum that will apply to any plant that we're growing. We need to first understand where those points are in general for any plant, and then we're going to just look at how different crops and different soils will change how we interpret those numbers and we apply them, but we still have to understand where those thresholds are. So on the low end, we can have a soil that we would consider to be absolutely bone dry. Either we haven't had any rain out in the field for weeks, we're having a drought, or we take some of the grow medium that we grow in, we put it in the oven, we bake it, we drive all of that moisture off, so we have on one end absolutely dry, except for the fact that it's not absolutely dry. You will still have water molecules binding to the surface so strongly that we cannot even drive them off of the surface. We will see that out in desert soils and in grow rooms and in bags of peat moss, but some of those bonds of water to surface particles are so strong, even when you think there's absolutely nothing there, you can actually have some moisture in that. But on one end, we have absolutely dry. On the other end, the first threshold that we want to understand is this threshold of saturation. And if we remember soil structure, we know that it's made up of sand, silt, organic material, and about 50% of the actual total volume of a sample of soil is actually air spacing. It's going to vary a little bit on what type of soil it is, but somewhere in that 40, 50, or even a little bit more percentage of a volume of soil or grow medium is actual air space or pores. We can have large pores, as we have in a big sample of large gravel, or we can have incredibly small spaces in clay and silt. But we still are going to have a lot of pore space. If we start watering this container, whether it's a pot or we're in a field and we're either irrigating or we get a lot of rain over the course of days, we're all familiar with the situation of soil being saturated. And what saturation is, it's a state in which all of the pores within that sample, whether it's soil or in the field or in a container, all of the pore spaces are absolutely full of water. And if you put any more water in, there is no place for it to go. It will pool on the top and it'll gradually start to run out, but there's no pore space left. So this is threshold number one, saturation. But whether you're out in a field, you're a field grower, or you're a greenhouse operator or a grow room operator, we know what happens when a sample gets saturated. the first thing we'll see if we're greenhouse growers is the water will start to drop down through the pot and come out the bottom of the pot. This, as we talked about in the last video, is that gravitational force acting upon the water. Gravity is actually pulling that excess water down through the structure of the grow medium or the soil, and it will start to clear some of the water out of the larger pores, so that you actually start getting a little bit of aeration within the soil. We also know that we don't want to try to grow successfully in a fully, continually saturated soil. The reason being that we need some gas exchange within the soil between the roots and the soil for optimal growth. If all of the pores are full of water, that gas exchange can't happen, and we develop what's called an anaerobic situation in the soil. Anaerobic basically meaning without air. So that can lead to some very dramatic negative impacts on the plant, inability to carry on proper organic reactions, gas exchange, which needs to happen within a root system. So an anaerobic situation is not a beneficial one to plant growth. However, when soil is saturated, we are also at a state where the soil suction or the soil matrix potential is actually at a point of about 0. So the plant can very easily take water up. It's just like, hey, we're not running into any resistance. So at a saturated point with a soil matrix potential of around 0, the plant can very easily take up water, but we don't want to stay in that situation very long. I was saying a short while ago, we're all familiar with what happens after you've saturated, say, a container with a grow medium in it, or if you're in a field and you're a farmer that's used to being out in your field looking at your soil. We have a saturated situation. In the field, it might be it's been raining or you've been irrigating so long that water is now starting to puddle on top, and it sits there for a little while. But that water will start to be drawn down by the gravitational forces, so that in the field, after about a day or 2 or 3, depending on the structure of the soil, you will actually have had the excess water drawn down through the soil matrix by the gravitational forces, and you'll have now soil pores that have oxygen in them. This next threshold is a critical one for us to understand. This is called field capacity. This is the field capacity threshold. It's the point in a field a day or 2 or 3 after a large irrigation event or a heavy rain event that has now caused puddling, and over the next day or 2, gravity has started to draw that water down and to open up some of the pores and allow oxygen and gas exchange to occur. Again, field capacity. If you're a greenhouse grower or a grow worm operator, when you water your containers, you should be following that 20% rule, where you put in water, get the soil saturated, put more water in until about 20% of what you've put in total in the top runs down through. We'll talk about why that's important soon. But you'll see after the course of an hour or 2 that you've had gravitational drainage and the plant taking up water to where you've reached that field capacity within less than an hour. But they're the same concept. It's going from saturation to gravitational forces pulling some of that excess water out so that you've now redeveloped some air spaces within those pores. Field capacity. Now, field capacity is really important to understand, because when we look at the relationship between field capacity and soil matrix potential, remember how we said as the water in the soil decreases, the soil matrix potential increases because there's less and less loosely held water, and that the more tightly the water is held, the harder it is for the plant to get that water out. When we're at saturation, we're at a soil matrix potential of around 0. When we get to the field capacity, the soil matrix potential is still very low in the single numbers. What that translates to is that it's very easy for the plant to get water out, get the nutrients up when we're at that very low soil matrix potential range. So in terms of optimal availability of water, ease of the plant getting water out of the soil and using it for its biological functions, field capacity is actually the optimal place for a plant to be in terms of the least amount of stress on that plant. And by stress, we mean exerting energy to try to get that water out of the soil. So field capacity is the threshold for optimal performance. The key now is understanding how far below field capacity we can go before we start inducing stress, which then translates to lower productivity, lower quality, and potential financial and biological damage to your operation. And this is where I see probably one of the largest or the most common problems that I run into in grow operations when we're doing scientific evaluations is lack of understanding of where the operation should be in terms of its irrigation thresholds, and that soil moisture levels within the containers or the medium that they're growing in is often dramatically lower than it should be, and that they're inducing significant stress on their plants. And understanding field capacity, when we start looking at the specific crop that you're growing and the specific soil, is going to become a very critical factor, because we can look at field capacity for a sandy soil. The field capacity might be a reading of, this is a volumetric water content sensor, we may want a reading of 20% when we're looking at a sandy soil. We may be at field capacity at 20%. For a clay soil, that may be way up around 40%, give or take some. So we'll look at the threshold, understanding the thresholds here, and then we're going to translate them to your specific crop. So we have saturation, threshold number 1 to understand. Field capacity, threshold number 2. And again, field capacity is going to be in the field 1 to 3 days after a large irrigation or a heavy rainfall situation. In a container in a greenhouse, we may be, less than an hour after saturation. So then the next critical threshold for you to understand is going to be one called the permanent wilting point. what the permanent wilting point is a point where the soil matrix potential, the soil suction, the water retention forces within the soil exceed the plant's ability to get water out of the soil, which basically will shut down the biological function within the plant. And if we stay at a permanent wilting point, the plant will die. So we have saturation, field capacity, permanent wilting point. For you as growers, we now have to understand, where do we need to be in that continuum for the crops that we're growing? And again, I can't emphasize this too much, that when I go into grow operations that are having issues, one of the absolutely most common issues I find is that they are way off of where they should be in terms of maintaining that volumetric water content or the soil matrix potential in the optimal range for their plants. Very often they're way below it, which is causing stress on the plants, which is causing a reduction again in productivity and quality. So saturation, field capacity, permanent wilting point. So the next threshold and concept for us to understand is one called total available water. And this is the amount of water that's in the soil that's actually available to that plant can actually pull out of the soil and use for its biological functions and to produce the crop and the quality that we're looking for. So total available water. This one's a pretty easy concept, because what total available water is actually just the field capacity number minus the permanent wilting point. So you might be saying, okay, so what do I use for numbers for field capacity, permanent wilting point? These are numbers that are available through the USDA, your extension service, some of the university agricultural departments. And as a reference, I'm putting up some figures that were done by University of Oklahoma Extension Service on numbers for the soils in their area, which will be very similar to, if we take New England soils and we look at things like sandy loam, loamy sand, clay loam, a lot of the figures in the analyses would be similar. So you can look at these numbers and get an idea of the numbers that we were talking about, would be talking about for New England, even though these are for Oklahoma, but you can get these numbers from University of New Hampshire or USDA. So let's look at a couple of figures here just to give you an idea. You can see that we're looking at, on this table one, typical soil water thresholds for different soil textures sampled across the U.S. It's giving you the soil texture. In the first two videos we did, we talked all about soil texture and what that means. We had sand, loamy sand, sandy loam, loam. So a lot of what we deal with around here is going to be in that sandy loam, loam, clay loam. That's a very common soils for New England. So if we look at field capacity, you can see how sand, the field capacity, is very low because the pore sizes are large and the the soil just doesn't hold much water. It clears very rapidly from gravitational forces. As we get up into the loams, the numbers start going up again because the particle sizes get a little smaller. If you see like the sandy loam or the loamy sand, it's got a field capacity of 16%, but if we do a sandy clay, we're up around 32%. The particle size is getting smaller. The surface area is increasing, which means that the surface binding capacity is much higher, so you'll have much more water being held by the soils, and the plant finds it more difficult to get it out of those soils, even though the soil can hold more water. So we have figures for field capacity. Then you can see where we have figures for the permanent wilting point. And you might be asking, well, what numbers are they using? Those numbers are coming from readings from instruments that are basically taking the volumetric water content. This is one from a company called Vegetronics. I'll put the link on. It's a little meter. I use it in my work in the field a lot. It's taking volumetric water content readings, which are the numbers that you're seeing in this chart. So if we look at something like loam, the field capacity is 27% volumetric water content taken right off of this. It means 20% of the volume of that soil is water. The permanent wilting point would be at a reading of around 12. If we're looking at total available water, remember that we're just taking the field capacity number minus the permanent wilting point, and that gives us total available water. But a thing to remember is that stress being imparted to the plant starts occurring way before we start reaching that permanent wilting point. In fact, how do we calculate where that point might be? So stress starts happening long before we reach that permanent wilting point. And we, as growers, whether we're field growers or greenhouse growers or grow-room operators, this is going to become the heart and soul of what we're trying to understand here today. Is we know that field capacity, up around field capacity, is the easiest, least stressful point for our plants to be at in terms of soil moisture content within the grow medium that we're using, whether it be field soil or grow medium within the greenhouse or the grow chamber. We know that permanent wilting point is where we're looking at imminent death if we stay there for the plants. So how do we know where to be in between those two numbers? We can calculate the total available water by taking field capacity minus permanent wilting point. But that just means that if we're close to the permanent wilting point, the plant technically can be pulling a tiny bit of water out of that soil, but it is so stressful that the plant is barely functioning and will die quickly if we stay at that point. So where do we need to be? You'll have people saying, well, my buddy told me to, feel the pod here, or my buddy told me stick my finger in if the top's perfectly dry, or a farmer will say, well, I water when, this weed starts to wilt. We have to, as science-driven growers, we have to know what point it is, so we don't need to be guessing or rolling dice to figure out where we should be or want to be. We have the science, we have the numbers, it's very simple, and it's going to make a huge difference in your productivity and your quality. So, we've looked at the threshold concepts for all plants that we need to just understand before we start talking about particular crops that we're growing. Saturation, field capacity, permanent wilting point, total available water. Simple, there's nothing really complicated about them. Now, we want to start looking at how does that relate to us as growers for the particular crops that we're growing. So we now look at probably the most important concept to understand. This is a concept called management allowable depletion. So don't get worried about how complicated this is going to get. This is very simple. Again, you understand saturation, you understand field capacity, you understand permanent wilting point. They're all straightforward concepts. Total available water is just field capacity minus permanent wilting point. We can find those figures through either your research departments at your extension service or the USDA. So now we just want to look at this final piece of the puzzle, this management allowable depletion. What we need to do to calculate the managed allowable depletion, just a couple of simple things. Number one, define what crop it is that we're growing. Number two, just know the basic figures, this field capacity, permanent wilting point, total available water, for the soil type that you're growing in, whether it's a field soil, a loam, a sandy loam, or a commercial grow medium. So type of plant and the characteristics of the soil that you're growing within. So I'm going to put up a couple of tables here. And what these tables are basically showing is that different crops, different plants have different tolerances to the amount of moisture that they need available in the soil and how easily they can get that moisture out of the soil. You all are familiar with if you'll get drought times and you're growing in your garden and you won't get any rain, you'll go out, your lettuce and some of the leafy crops will be laid right over and they're all drying up and wilting, and some of your other plants are just looking droopy. And then you've got some weeds over here that are like just going gangbusters. They looks like they actually relish the dryness. That is an example of the difference in tolerance of moisture levels between different crops. We have to understand that even within commercial crops, vegetable crops, medicinal crops, that different varieties, different species of plants have a different tolerance to how well they can manage higher or lower soil moisture levels. So that information, just like the information on soil structure, is available in different sources, USDA, Extension Services. And if we look at the first one, we're looking at this table 3 from University of Oklahoma. Management allowable depletions and maximum root zone depths for selected crops. You can see that it'll say cotton 0.65, rice 0.2, citrus 0.5, lettuce 0.3. What those 0.3, 0.5, all of this is referring to, what those percentages, like for cotton where it says MAD, management allowable depletions, and it says 0.65. that 0.65 is percentage. They're saying 65%, lettuce is 30%, but what's that a percentage of? That's a percentage of the total available water for the soil that you're growing in. So let's take a look at what this means to you as a grower with all of these numbers that we've been throwing around. Again, we've looked at saturation, field capacity, permanent wilting point, total available water. Now we're looking at management allowable depletion rate, which is what's going to be, that's going to be the number that is going to be the initiation target for your irrigation protocol. So your field grower, you have, let's go back to table 1 and pick a soil. Say you've got a sandy soil, a sandy clay loam with a field capacity of 36%, a permanent wilting point of 16%. That means you have a total available water of 36 minus 16, or 20%. That's the numbers for the type of soil that you're using. Now, we have to specify that to the crop that we want to grow. So let's say we want to grow cucumbers. We go to table number 3, which gives us the management allowable depletion rates for different crops. We come down to the bottom, it says cucumbers with a management allowable depletion rate of 0.5 or 50%. What that means is that when we take the total available water figure for our sandy clay loam, which is 20%, multiply that by 0.5 to get 50%, because that's our management allowable depletion rate for cucumbers. That gives us 10. It means that 10% is the maximum amount of water we can drop below that field capacity figure for our soil, which is 36%. We can only drop 10% from that 36% before we start encountering severe stress on the plants, which is going to translate to suboptimal production. So we have 36 of a field capacity. We can only drop 10% from that, which gives us 26%. That means if we're watering out in the field and we're using a volumetric water content sensor, when we put that sensor in the ground, if that sensor is between 26 and 36% volumetric water content, we are in an optimal range for productivity and health for that cucumber crop. If we're at 20%, 21%, 18%, it means that the plants may be pulling water up, but not at an optimal rate, which then that's going to translate to a drop in quality and productivity. Your yield is smaller, your return on investment is smaller. When I'm out in the field and I bring my soil sensor, my soil moisture sensor meter with me, I very often am getting figures in the teens, middle teens, low teens sometimes, and farmers will say, well, I didn't want to quite, they look like they were a little bit. If you're below these data-driven figures, you're losing productivity, you're losing quality, and you're losing money. If we were growing a different crop, say we wanted to grow lettuce in that same soil. So we look at that same soil, we have a field capacity of 36%, permanent wilting point of 16. We have a total available water of 20%. Say we want to grow lettuce. We look at our chart again. Now lettuce only has a 0.3 or a 30% management allowable depletion rate. So now if we take 30% of that total available water of 20%, 10% would be 2, 4, so 30% of that 20 would be only 6. So now, if we take our field capacity of 36, now we have a management allowable depletion rate of only 30. We have to be at 30% volumetric water content when we take a reading. If we're at that 26 that we use for cucumbers, we're in a state where the lettuce is now suffering from quite severe water stress, even though it is at a level that the cucumbers are fine. The cucumbers have a higher tolerance. They have a greater ability to pull water out of a soil with a higher soil matrix potential. So using a volumetric water content sensor is critical, but it has to be linked to understanding what those thresholds are for the soil type that you're growing in, but also it has to be linked to the specific crop that you're growing within that soil. Because if we just pick one number and say, well, I've grown cucumbers in this plot for a long time, and I've always used, I've used, 26 as my soil moisture irrigation threshold, and you transfer that over lettuce, now you're going to be growing suboptimally, and you're going to be having negative impact on growth rate, size of the crop, quality of the crop, which translates again to lost return on your investment. So irrigation protocols have to be driven by soil type and the published data figures for your particular type of soil: saturation, field capacity, permanent wilting point, total available water, management allowable depletion rates. Those all relate to the soil that you're growing in. But then you also have to make sure that you're looking at the specific management allowable depletion figures for the crop that you're growing, because using the figures for one crop for another crop can very well cause you a reduction in crop size and crop quality. So if you're a greenhouse grower or a grow room operator, I can't emphasize enough how important this little tool is. It's I can't go anywhere if I'm doing analysis in a grow operation, whether it's outside or inside, greenhouse, grow room operation, field, without knowing a couple of things. For indoor grows, I have to have a quantum meter with me. I have to have a pH and EC meter with me, and I have to have a volumetric water content meter. As we were saying before, there are meters that read in soil matrix potential, but volumetric water content meters are much more common, a little bit easier to understand, and a little bit more universal. I see grow operation after grow operation after grow operation using basically not having an irrigation protocol and just going off of anecdotal info of my buddy told me to do this, or I saw somebody said do that, or a guy at a show told me to do this, or my brother told me to do this. That's fine if you're just a hobby grower, but if you want optimal results and you're a commercial grower, you have to be growing using science, using data, because that data and the science is there to help you maximize productivity and quality, which translates to optimization of your business plan and your return on your investment. Can also, for you field growers, these can be used in your field operations or in your greenhouse operation with a sensor in place, either in the field or in containers. They have a little Wi-Fi system with this that can just broadcast to a very simple little hub, inexpensive little hub that can notify you on your phone about what's going on, and that can actually automatically initiate irrigation, turning on and off irrigation systems very inexpensively. The thing to remember about, or one of the things to remember about any in-soil sensor, is that you want the sensor to be at the root depth that the particular crop that you're growing normally puts down. And if we look back at one of the charts here I had put up for you, they give a range for the maximum root depth of those plants. So, because if you put a sensor, any company sensor, in 2 inches on the surface, and you do a deep irrigation, and then you get a couple of really hot, dry days, and the first 2 or 3 inches of the soil dries out, and the number goes, the sensor number goes way down and initiates irrigation, even though if you dug down 6, 8, 10 inches, there would be plenty of water to still be within that depletion range. You would be not using the sensor efficiently or correctly and initiating irrigation at an inappropriate time. So make sure that you have your sensor depth correct, and that if you're in an outdoor field operation, it's always best to have multiple sensors that can average out different areas in your field, because all of you know that you've got areas in your field that run a little drier, that run a little wetter, so that you can fine-tune your sensors. But it's a very inexpensive system to put in that can save you a lot of money. A thing that I will mention for you indoor growers, especially some of you medicinal growers, I get a lot of questions on this whole process of crop steering. People come to me and say, well, geez, I'm going to start doing this crop steering. My buddy told me it was really good. And I'll just ask them, what are you going to do? Well, I'll give it a little bit here, and then I give it just a little bit then, and I give it. If you actually look into this whole process of crop steering, it is very precise. It cannot be done without multiple sensors, data tracking, and precision triggering points. If you, I'll put up just a graphic here from one of the companies that sells equipment for doing crop steering, and it'll give you an idea of how precise it is. They don't talk by give it a little bit here and a little bit there. It's at X number of minutes, drop your volumetric water percent down 3% here, up it by 5% there, down by 7% here. It's extraordinarily precise. So if you're looking at looking into this process of crop steering, understand that it can't be done by the seat of your pants. It's a very precise data and instrumentation driven process that my suggestion would be to first get really good at doing your own measurements and understanding the science of irrigation before you take that leap and say, now what I'm going to do is I'm going to put in a full-blown crop steering system, because it requires a lot. It's not a simple system. It can work really well, but only if it is done correctly with the correct equipment, the correct data gathering, and the correct analysis. So once again, we've covered a lot of territory in this video. The last three videos, well, this is number 4 on irrigation. I hope some of you take the time to watch them and understand how critical this is to your operations. Sometimes I get comments of, why are the videos long? Why do you cover so much science? It's because I'm a scientist, and my function is to help people grow optimally. Because if you're in any type of agriculture, any type of business, you work hard, you put a lot of time, you put money in, a lot of effort. It's 24/7. And my function is to try to help you understand that the science is there not to make you feel like, oh, well, I got to study this or it's going to get me confused. It's there to help you use your time better, which will result in higher crop yields, higher crop quality, lower labor input, lower financial input, and a better return on your money. The science is there as a good thing for you, a positive. It's there to help you. If you have questions, get in touch with me. If I haven't got the answer, I'll put you in touch with the people or the data or the reports that do. And again, just understand that science is your friend, and it's your business ally. It's not there to be problematic to you. So I've enjoyed this series. I'm probably going to do a little series coming up soon on understanding some of the science of lighting, both for casual hobby growers and for commercial growers. There's a lot of misinformation and misunderstanding in that area too. So keep an eye open for that. I've got a lot of videos in line here. So hopefully you've enjoyed this one. If you have any questions, get in touch with me through the Gmail address. I'd be glad to get back to you with any info or answers that might be helpful. So we're actually approaching the Christmas season at this point. So I hope that all of you will have a good holiday season. Remember to be good to each other, and remember, you need to know what your plants need to grow.